In this section, we're going to be going over implicit differentiation. So far when we've been taking derivatives of functions, we already had y solved for. So for example, we would have something that says, take the derivative of y equals 3x plus 2. Now, when we're taking the derivative, we are not going to have y explicitly solved for, and that means these functions are going to be defined implicitly. So an example of this is like this right here, x squared plus y squared equals 25. So that, it doesn't actually represent a function because that's a circle, and circles are not functions because they failed the vertical line test. But this is a relation, and we could take the derivative of this, but it's going to be using implicit differentiation. So for this particular one, we could solve for y. Some of them we will not be able to solve for y. So let's actually just go ahead and see us solve this for y. So we have x squared plus y squared equals 25. If we solve this for y, we need to subtract x squared to the right. So that's y squared equals 25 minus x squared. And then we need to take the square root of both sides to get y by itself. But when we take the square root, we have to remember that we get plus or minus on the other side. So it's y equals plus or minus the square root of 25 minus x squared. So we could think of this as two separate functions because of the plus or minus. And those two functions would be, one of them is the positive one, the other one's a negative one. So we can say, let's let f of x be positive square root 25 minus x squared, and g of x be negative square root 25 minus x squared. And you can see here, the pictures here, the one on the left is x squared plus y squared equals 25. That's the circle, that's the equation that we started with. And then you could see when we let f of x and g of x be two separate halves of that circle, we have the top half for f of x, the positive version, and then we have the negative version for g of x on the right. So this particular one, we were able to actually solve for y, and then we could have taken the derivative of both of these separately, but we're not always going to be able to solve for y explicitly. So let's take a look at the volume of Descartes. So this is just one of the kind of famous family of equations that cannot easily be solved for y. And just for some fun facts, folium comes from the Latin word for leaf, and if you take a look at the graph, you can see it kind of looks like a little leaf. Okay, so one example of the volume of Descartes' equation, like I mentioned, it's a family of equations. One example is this right here. X cubed plus y cubed equals 6xy. And here is the graph of it right down here. So there's actually a slant asymptote right there for the graph, just kind of another interesting feature of it. So this is what this particular volume of Descartes' equation looks like. So you can see here, if we were trying to solve this for y, it would not be very easy. So thankfully we don't have to solve these for y, and now we're going to introduce implicit differentiation for when we're trying to take the derivative of something like this right here. Okay, so implicit differentiation, to take the derivative of a function that's not solved for y, we are going to be using this method. And this method is going to be differentiating both sides of the equation with respect to x, and then solving for y prime afterwards. So we're going to differentiate both sides of the equation and then have to solve it for y prime. And something to keep in mind, I'll write it up here, we need to use chain rule when differentiating a term with a y. And we'll see how we do that in this next example here. Okay, so example, if x squared plus y squared equals 25, let's find dy dx. This was the first example on the first page. So what we're going to do is we're going to take the derivative of both sides of the equation with respect to x. So that's going to be d dx of that whole entire left side. So it's the derivative of that whole left side with respect to x equals d dx of 25. So that's basically how we're going to start these questions every single time. So the derivative now of, let's take a look at the left side. The derivative of the left side, we're going to go term by term. The derivative of x squared is just 2x. Right, derivative of x squared is 2x. Now here comes kind of the new part. We need the derivative of y squared. So the derivative of y squared here, this is going to be chain rule. So remember chain rule. Chain rule is if we have the derivative of the composite of two functions, f of g of x, the derivative is going to be f prime of g of x times g prime of x. So the derivative of the outer, leave the inner alone, times the derivative of the inner. So the inner function here for y squared is y. The derivative of the outer is going to be using power rule for that exponent of y squared. So we're going to bring down the exponent, subtract 1 from the exponent, times the derivative of the inner. The derivative of the inner is the derivative of y, which is dy dx. Okay, so that's kind of the confusing part, so get used to seeing this. We essentially take the derivative of it just like you would for x, and then there's going to be a dy dx afterwards. Okay, and then the derivative, easy part, the derivative of 25, that's a constant, so the derivative is 0. Okay, so that's our result after we take the derivative of both sides. Now we have this added step of actually solving for y prime, in this case denoted dy dx. So all we have to do is subtract 2x to the right. We get 2y dy dx equals negative 2x after we subtract that to the right. And now we can divide both sides by 2y. So that's dy dx equals negative 2x, negative 2x over 2y. And the 2's cancel. So we get dy dx equals negative x over y. Okay, so there is our y prime, or our dy dx. Next question, let's find the equation of a tangent line to the circle at the point 3, 4. So equation of a tangent line, we should say, okay, point slope formula, y minus y1 equals m times x minus x1. We are given x1, y1, the point on the circle, in this case, 3, 4. We need the slope. The slope is going to be the function, the derivative of the function evaluated at x equals 3 and y equals 4. And let's write this like this. It's going to equal the derivative evaluated at x equals 3 and y equals 4. Okay, so that's just some notation that I believe we've seen. So we have the derivative right above us. All we have to do is plug in 3 into x, 4 into y, and we get negative 3/4. So we have our point, we have our slope. Let's go ahead and plug in. That's going to be y minus 4 equals negative 3/4 times x minus 3. And maybe let's just go ahead and solve this for y just so it looks a little nicer. And if you solve that for y, you should end up getting y equals negative 3/4 x plus 25/4. So let's just draw a quick little diagram, quick little graph of what we actually just did. Here is our circle, x squared plus y squared equals 25. We should know that that's centered at the origin with a radius of 5. And we wanted the equation of the tangent line at the point 3, 4, which I'm just going to say is about right here. And we just found that that line has the equation y equals negative 3/4 x plus 25/4. Okay, so let's do a couple more examples here. Let's find y prime if x cubed plus y cubed equals 6xy. So we're going to start this off the same way. We are going to take the derivative with respect to x on both sides of the equation. So d dx of the left side equals d dx of the right side. And now let's go ahead and take the derivative of the left side. The left side, we have two terms, x cubed plus y cubed. The derivative of x cubed is 3x squared. Now the derivative of y cubed is going to be chain rule. So that's 3y squared times the derivative of y. Instead of using dy dx here, I'm going to use y prime, and I'm going to kind of tilt the apostrophe for the prime a little bit just so it doesn't look like a 1. That's one of the reasons why we don't use it a lot, is because it kind of looks like a 1 when you're doing it by hand. That's supposed to be y prime. Okay, so that whole left hand side, same thing as before. You do the derivative with respect to x, so you need the y prime there. Okay, and then on the right we actually are going to have product rule. And just to make it a little bit cleaner, what I'm actually going to do right here is I'm going to bring this constant of a 6 out front. So let me just go ahead and rewrite that as 6 times d dx of xy, x times y. And now we'll do the power rule. So I'm just going to rewrite that left-hand side. We didn't do anything to it. Just kind of reorganizing the right-hand side. So we're going to have 6 times, make sure you have parentheses. Power rule, remember, is the first times the derivative of the second plus the second times the derivative of the first. So that's going to be the first times the derivative of the second, so x times y prime, plus the second times the derivative of the first. The derivative of x is 1. So we're taking the derivative with respect to x. That's why that derivative is 1. And the derivative of y is whatever y prime is. So now we need to solve this for y prime. So it seems kind of confusing, but if we're solving this for y prime, technically it's the same way we would solve linear equations. Let's first distribute the 6 on the right. Okay, so we distributed the 6. Now everything with a y prime in it, let's get it to the left-hand side of the equation. Everything without a y prime, let's get it to the right. So let's subtract this term to the left, and let's subtract this term to the right. So we're going to end up with 3y squared y prime minus 6x y prime equals 6y minus 3x squared. So everything on the right hand side does not have a y prime. Everything on the left does. The reason why we did that is because now we can factor out a y prime. If you factor out a y prime, you're left with 3y squared minus 6x. And then the right hand side stays the same. And hopefully now it becomes clear. All we have to do is divide both sides by whatever's in these parentheses, and we get y prime equals 6y minus 3x squared over 3y squared minus 6x. So there is the derivative. And if you really want to, it looks like you could factor out a GCF of 3 in the numerator and denominator separately and then cancel that common factor of 3. I'm just going to leave it like this. Okay, let's go ahead and find the tangent line. Find the equation of the tangent line to this folium of Descartes at the point 3,3. So that's what this was, what we just did. This was the folium of Descartes example that we saw a few pages ago. So there's the derivative, and we want the equation of the tangent line. So we have point slope form. We have our x1, y1, which we know is 3,3. And now we need the slope, which is going to be the derivative evaluated at 3, 3. So I'm going to write that as dy dx evaluated at x equals 3, y equals 3, and we go ahead and plug everything in. That's 6 times 3 minus 3 squared over 3 times 3 squared minus 6 times 3. And we evaluate this. And we should get -1. So let's go ahead and plug in. We have y minus 3 equals -1 times x minus 3. And let's solve this for y. We get y equals -x plus 6. So we have the graph right over here. So we should say to ourselves, does that make sense? And yes, it does look like it makes sense because clearly this has a negative slope and a positive y-intercept. So -x plus 6 seems reasonable. So something a little bit harder here, we want to know at what point in the first quadrant is the tangent line horizontal. That means when does y prime equal 0? When is the slope of the tangent line equal to 0? That is a slope of a horizontal line. So what we're looking for, so here's the graph of the volume of Descartes, that function that we have, or not a function, the equation that we have. We are looking for, it looks like maybe about this point right here. So we're in the first quadrant, and it looks like that point will have a horizontal tangent line, right? So we're looking for that point right there, the x value and the y value. So what we are going to do is we're going to set y prime equal to 0, and we're going to solve it. So let's go see what y prime was on the previous page. So here's y prime right here. We're going to set that equal to 0. So we get our function set, our derivative set equal to 0, and we're going to solve this. So you should be saying, well, what are we solving for? We have an x and a y. What we're going to do is let's solve this for y, and then let's kind of go from there. So let's solve this for y. A little bit easier than it looks, because if we cross multiply, if we multiply this denominator to the right, it's going to equal 0. So the only way this whole thing equals 0 is if the numerator equals 0. And for this numerator to equal 0 now, we solve this for y. We can add 3x squared to the right, divide both sides by 6. 3 divided by 6 is 1/2. So that gives us x squared divided by 2. So it doesn't really, it helps us a little bit because we're going to be using that, but that doesn't tell us an x, y ordered pair, right? So what we actually need to do is we need to go back to the original equation. So this was the original volume of Descartes, x cubed plus y cubed equals 6xy. And we are going to take this and substitute that in. Okay, now we can see that we have these two equations with two variables, which means hopefully we can solve for both of them. So let's go ahead and do that. Let's plug in everywhere there's a y. We're going to replace that with x squared over 2. And we get x cubed plus x squared over 2 cubed equals 6x times x squared over 2. Now we have one equation with one variable, so we can solve for x now. So let's go ahead and simplify both sides a little bit. We get x cubed plus x to the 6th over 8. So x squared cubed, multiply the exponents, 2 cubed is 8. And on the right-hand side of the equation, we get 6 divided by 2 is 3. X times x squared, x cubed. And now what this is just a polynomial equation, essentially. So let's get everything on one side of the equation and factor if we can. So I'm going to subtract 3x cubed to the left, and that's going to give us x cubed minus 3x cubed, which is negative 2x cubed. And now we have the set equal to 0. So now let's go ahead and try to factor. we can factor out a x cubed. And actually, before we do that, we can actually get rid of these fractions. If we multiply both sides of the equation by 8, because that's our denominator, we get x to the 6th minus 16x cubed. 0 times 8 is 0. So that just gets rid of the fractions. It's kind of nice. And now we can factor out the x cubed. We're going to be left with x cubed minus 16 equal to 0. And we get two things here, right? We get x cubed equals 0 and x cubed minus 16 equals 0. So the first one obviously gives us x equals 0, but this one we actually can omit because 0 is not in the first quadrant, which is what the question is asking. It says first quadrant, so x equals 0 is not in the first quadrant. It's right on the line. So we omit it. I'm going to put not in quadrant 1. And let's solve the one on the right. The one on the right, we get x cubed equals 16. We take the cube root of 16 now. So that's going to be the cube root of 16. So we can either write that as the cube root symbol, or we can write it with a 1/3 exponent. So the cube root of 16 is, I don't know, 2 point something. Either way, we know it's in the first quadrant because, well, we know the x value is in the first quadrant so far because it's positive. Let's figure out what the y value is. And to figure out what y is, all you have to do is take this and you can plug it right back into here because we already have y nice and solved for. You could also plug it back into the original equation, but that's going to make it more difficult to solve for y. So just solve it in, plug it into there. And if we do that, we're going to find the y coordinate. As you can see, I put it down here. The y coordinate is 16 to the 2/3 divided by 2. So that is our coordinate, 16 to the 1/3, comma 16 to the 2/3 divided by 2, which is a little messy. And if we evaluate that, we get 2.52, comma 3.17, which is obviously in quadrant 1 because they're both positive. So this would be the x coordinate, 2.52, and then this y coordinate over here, 3.17. Okay, so a little bit more complicated with that one. So a couple more examples. Let's find y prime if sine of x plus y equals y squared cosine x. So here's just a little graph of it just so we can see how things start to look a little weird, especially with these implicitly defined functions. So let's go ahead and write this down again. So I have room sine x plus y equals y squared cosine x. Okay, so on the left, now we're going to take the derivative of both sides, so let me write that. It's good to write this step even though we know that's what we're going to be doing. You should still write d dx of both sides. So the derivative of both sides with respect to x. And let's go ahead and do that. So the left one, sine of x plus y, that's going to be chain rule first. So it's going to be the derivative of the outside, which is the derivative of sine, which is cosine. Leave the inside alone, times the derivative of the inside. The derivative of x plus y is the derivative of x, which is 1, plus the derivative of y, which is y prime. And then the right-hand side is going to be product rule, y squared times cosine x. So it's going to be the first times the derivative of the second, derivative of cosine is negative sine of x, plus the second times the derivative of the first. The derivative of y squared is 2y y prime. So don't remember that chain rule with the y term. And now we have the fun part of solving this for y. So before we solve it for y, we should distribute this cosine of x plus y. That's going to give us cosine of x plus y times 1 plus y prime times cosine of x plus y. And on the right-hand side, we have negative y squared sine x plus 2y y prime cosine x. Just cleaned it up a little bit and rewrote it. And now we're going to do the same thing that we did previously. We're going to get everything with a y prime on the left, everything without a y prime on the right. So that means we're going to subtract this term to the left, and we're going to subtract this term to the right. So it's going to end up being y prime cosine x plus y minus 2y y prime cosine x on the left equals negative y squared sine x minus cosine x plus y on the right. And now on the left, let's factor out that y prime, and we're going to be left with cosine x plus y minus 2y cosine x. And the right side stays the same. And all we have to do now is divide what's in these parentheses, and that will give us y prime by itself. So y prime is going to equal that right-hand side divided by what was in those parentheses. So that technique is pretty common, where you get everything with a y prime on one side and everything without a y prime on the other side, factor out the y prime, divide by what was left over. Okay, let's do maybe one more of these examples. We're going to find y double prime if x to the fourth plus y to the fourth equals 16. So this actually looks harder than it is. Let's go ahead and apply our rules. Let's take the derivative of the left side, d dx of x to the fourth plus y to the fourth equals d dx of 16. And the left-hand side, the derivative of x to the fourth is 4x cubed. The derivative of y to the fourth is 4y cubed times y prime. And then the derivative of the right-hand side is 0. So that's why this one it may be a little bit easier than it looks like, because anytime you have a constant on one side, it's going to be 0 after you take the derivative. Now solving this for y prime, all we have to do is subtract 4x cubed to the right, and then divide both sides by 4y cubed. Notice that the 4's are going to cancel. We're going to be left with x cubed negative x cubed over y cubed. Right? 4's cancel, we still have the negative, so there's y prime. But now we want y double prime. We want the second derivative, so all we have to do now is take the derivative of both sides. So we're going to do d dx of y prime equals d dx of negative x cubed over y cubed. So the derivative of y prime is y double prime, which is why we did it. And now we need the derivative of the right-hand side. So now we actually need quotient rule, right? Because we have two things being divided. We have a fraction. You could write it as negative x cubed times y to the negative 3 if you want to use product rule. It doesn't really matter. So let's go ahead and do this. It's going to be, that negative is just going to be coming along for the ride out front. It's going to be low d high minus high d low. The derivative of y cubed is 3y squared times y prime, all divided by low squared. Y cubed squared is y to the 6th. Multiply those exponents. And maybe this is where it gets a little complicated. We know what y prime equals because we found it already. Y prime equals negative x cubed over y cubed. So let's go ahead and actually plug that in for it and see what happens. So we get y double prime equals negative, and I'm just going to rearrange some stuff so it looks cleaner, 3x squared y cubed minus 3x cubed y squared times y prime, which is negative x cubed over y cubed, all divided by y to the 6th. And let's try to simplify a little bit more. And let's go ahead and rewrite this as negative 3x squared y cubed. And it's going to be plus, because the two negatives over here on the right, x cubed times x cubed. We add the exponents. That gives us 3x to the 6th. And then we have y squared divided by y cubed. So it's going to be 3x to the 6th divided by y. And that's going to be over y to the 6th. So let's keep on going. Let's keep on simplifying this. We don't want this complex fraction. We have the fraction in the numerator of the bigger fraction. So the way we get rid of it is we multiply by the GCF. Or sorry, we'll multiply by, in this case, the y. That's going to be what cancels that denominator. So we multiply the numerator and denominator by the y. And we get negative 3x squared. We get y to the 4th now because we multiplied by y. And then that second term is going to be 3x to the 6th because the y's cancel. That denominator is y to the 7th. And maybe let's go one step further because something else actually happens that's kind of nice. If we factor out a 3x squared in the numerator, something nice is going to happen. Let me just get some more room here. Okay, there we go. Let's go ahead and factor out a 3x squared in the numerator. We're going to be left with a y to the 4th plus x to the 4th all over y to the 7th. And the reason why that is nice is because what's in parentheses right here is the original equation. The original equation is x to the 4th plus y to the 4th equals 16. So we can replace y to the 4th plus x to the 4th with a 16. So it becomes negative 3x squared times 16 over y to the 7th. And now, after all of that, now we are done. We get y double prime equals negative 48x squared over y to the 7th. So you can probably see why it was kind of nice to keep on simplifying this one, because it actually turned out to look pretty nice. So before we move on to the short last thing for this section, here are just a couple unusual implicit functions and their graphs. You can take a look at these on your own if you want. They were just in the book, and I figured I'd throw them in because they're kind of look interesting, and you can see how with these implicit functions, things can look pretty funky. Okay, so here's the last thing, and we'll do 2 examples with this. It's the derivatives of inverse trig functions. So the inverse trig functions also have their own derivatives, and without going into detail of how we get them, here they all are. The derivative of sine inverse is 1 over the square root of 1 minus x squared. The derivative of cosine inverse is negative 1 over the square root of 1 minus x squared. Derivative of tangent inverse, 1 over 1 plus x squared. And then I'm sure you can read these off on your own. So try to get these memorized as well. They're not as difficult to memorize as it may seem because there's a nice pattern to it. As you can see, sine and cosine are almost the same, the inverses, except cosine is negative, cosine inverse. Okay, so let's go ahead and differentiate. We want to take the derivative of y equals 1 over the inverse of sine. So before we do that, we could use quotient rule, right? Because technically this is a quotient. But let's rewrite this as the inverse of sine to the negative 1. because sine is inverse is in the denominator, we can put it in the numerator. And something that's very important here, the reason why I did this -1 does not represent a number. That's the inverse. So that is sine inverse. This -1 represents the reciprocal, because we take it from the denominator, put it in the numerator. So even though they both have a -1, the inverse's notation does not actually mean a number. It's just unfortunate overlapping of notation. Okay, so let's go ahead and take the derivative of that. To take the derivative of that, we're going to need chain rule. So it's going to be the derivative of the outside, which is going to be bringing the -1 out front, leave the inside alone, subtract 1 from the original exponent, times the derivative of the inside. So now we want the derivative of the inside, which is the derivative of sine inverse. So notice the difference here. We now have negative sine inverse of x to the -2. And now this is where we need the derivative of sine inverse, which is right up here. Derivative of sine inverse is 1 over the square root of 1 minus x squared. 1 over the square root, 1 minus x squared. And we can clean that up a little bit by writing it as -1 over sine inverse squared times the square root of 1 minus x squared. So still messy, but maybe cleaned it up a little bit. So we might not be working with these a ton in this class, but down the road in a different class, you should have all of these memorized. If you memorize them now, your life will be a lot easier. Okay, let's do one more example. We're going to find the derivative of f of x, where f of x is x times arctangent of the square root of x. So first, we need to remember that arctangent is the same thing as tangent inverse. Same thing with arcsine, arccosine. Those is just another way that we can write the inverse function out. So let's go ahead and do the derivative. We want f prime of x. This is going to be product rule. So it is going to be first times the derivative of the second. So the derivative of arctan of the square root of x plus the second, which is arctan square root of x, times the derivative of the first. The derivative of x is 1. So this gets a little tricky. Let me just move this down so I have some room. There we go. We know that based on the previous page that the derivative of tangent inverse of x is 1 over 1 plus x squared, right? We're not taking the derivative of tangent inverse of x. We're taking the derivative of tangent inverse of the square root of x. So instead of this being x, it's going to be the square root of x, which you're going to see that this ends up simplifying to just x. So let me get rid of that just so we have it. So let's say we have f prime of x equals x times the derivative of arctan, the derivative of tangent inverse, is 1 plus the square root of x squared, and then plus arctan square root of x. So it's not always an x that you're plugging in here. These derivative definitions are not always set in stone. It depends on what that input is. In this case, it's the square root of x, so we have to adjust it a little bit. Okay, now we can simplify it, and then we'll be done. It's going to be x over 1 plus the square root of x squared. They cancel. 1 plus x plus arctan of the square root of x. Oh, wait a minute. Actually, I have to go back. I forgot the chain rule. Right here. Okay, so ignore everything I just said up to this point. So this is actually chain rule. So you can see how this gets a little complicated. Taking this derivative is technically chain rule. It's going to be the derivative of the outside, leave the inside alone, times the derivative of the inside. So it's going to be the derivative of arctan, which we just did. So that's why you leave the inside alone. You leave it as the square root of x. That's the derivative of the outside, leave the inside alone, times the derivative of the inside. So that's times the derivative of the square root of x, which is 1/2 x to the negative 1/2. So that's rewriting the square root of x as x to the 1/2 using power rule. Sorry about that. That was just me forgetting to use chain rule on that. And now we can simplify. So now we simplify it. And let's just simplify it in one step. We have x divided by x to the 1/2, which is going to be x to the 1/2 in the numerator, which is the square root of x, right? X over x to the 1/2 equals x to the 1/2. And then that's over this 2 times 1 plus x, for that same reason why we mentioned before with the square root and the squared canceling, plus arctan times the square root of x. Okay, so that is it for this section, I believe. Yep, that is it. So yeah, that last example, probably the trickiest. So try to memorize those definitions for those derivatives for the inverse trig functions, and you should be good for now. Okay, so that is it for 3.5.